Hi, today we are on Exam 3 Part B. And what we're looking at here is a cooling tower with water coming from the top and air being blown up from the bottom. And these might be some turbines here that to help move it upwards. We also have a distance of z in the downwards direction. This is the liquid flow rate, and this will be in kilograms per meters squared. And then this is the gas flow rate, which will be kilograms per meter squared. Alright, so then we also have the temperature of the water and the temperature of the air. And so what we're trying to do is we want to cool the water by evaporation, but if the water is fully saturated, then the cooling will be done purely by heat exchange between the water and the air, because if the air is fully saturated, nothing will be able to evaporate more into that air. Okay, and then what we want to do is we want to be able to plot the temperature of the water, the temperature of the air, and the mole fraction of water vapor in the air in respect to this distance z down the column. And so what we want to look at here is maybe just a specific area of the column. Let's use this color. So let's say we're looking at this area or this section of the column. We'll have air coming in and out of this section in the upwards direction, and we'll have water going in and out in the downwards direction. And we'll just call this lowercase a. So this is going to be our specific area, which is going to be in meters squared per meters cubed. And this is the ratio of the area to the volume. So this will be the film thickness. Let's see. The film thickness will be dz. And this is, what we're looking at here is how does the mole fraction change of the water vapor as it crosses through this section, through this region. And so what we can look at here is an equation. So what we want to look at is the area multiplied by the gas flow rate all over the molecular weight, and this is for the air, gives the moles of air and water mixture in the gas phase per second, this whole expression. And then if we want to look at it in regards to distance, this will give us the number of, multiplied, whoops. If we multiply this by that mole fraction, and then take the derivative in respect to distance, then we will be able to look at the number of moles of water passing through this cross-section. And we want to see how this changes and what causes this change. So we want to look at surface area. So now we want to look at the other side of the equation and in the perspective of having some packing in this column, which will lead us to the surface area. And at the surface area of this packing, you have some water or water vapor at the interface that is fully saturated and will evaporate into the air that is blowing through. Okay, so then on the other side of this equation, we want to have the mass transfer coefficient, the concentration of water at that interface, minus the concentration of the water out in the air, in that bulk air. And then also what I want to note is that we want to make this constant. So we're going to see little change, and we want to simplify this and take it out of the differential equation so we don't have to do the product rule. And so we're just going to keep this constant and make it easier by pulling it out. Okay, continuing on. We are going to look at that cross-sectional area, that specific area, and then we want to multiply it by the area times the distance. So this is going to be the differential volume right here, and then this will give us this the combination of these three variables is going to give us the surface area that's available. Okay. So then so that's how much interfacial area is available between the air and the water. And then so the last thing we want to consider is a negative sign here. And the z increases in the downward direction, and the mole fraction of the water will increase in the positive z direction, because this is the air feed, and obviously there's going to be more water up here. This is the feed air as you go down. But so the way it increases in mole fraction isn't in that downward z direction. So as you go down, the amount of contact the water has with the air decreases, which means that there's going to be less water vapor as you go down. So that's why we need that negative sign. So now what I want to do is I just want to simplify this part of the equation into one variable as a molar flux. So I'm going to write it as the molar flux of water, simplified an abbreviation of capital N, small w, and have that mass transfer coefficient out in front. And then I want to rewrite these concentrations in terms of partial pressures. And at the interface, looking at this first, at the interface, this concentration will be at equilibrium. And so we'll have a saturated vapor pressure of the water at the temperature of the water. So at the interface, we'll have equilibrium conditions, remember. So we have that saturated partial pressure at that temperature of the water. This is for the water. Put it over RT. And now looking at the concentration in that bulk air, we want to put that in terms of partial pressures too. So we're going to do that mole fraction multiplied by the total pressure, and that will give us the partial pressure of the water vapor over RT. Once again, that gas constant times temperature. And altogether, this will give us the concentration far away in the bulk air. And so now what I want to do is I want to combine and add this variable to this expression so we can get rid of this and simplify the equation in general. So what's going to happen is these areas are going to cancel, and I'm going to move this dz over with the dy because we are going to pull out this gas flow rate and the molecular weight out in front, like we talked about before. So that's going to give us dy over dz with that negative sign. Don't forget about the negative sign. The specific area, multiply that by that, oh wait, we just got rid of the area, multiplied by the molecular weight all over the gas flow rate. And then that new variable of the molar flux of that water. And so now this expression is going to give us the mole fraction of the water in of the water vapor in the air. All right, so what we know now is we have the first differential equation, and what we want to do now is we want to look at the changing temperature of the water and the gas phase. So thinking of the temperature changing, we want to look towards enthalpy. And the change in, we want to look at the change in enthalpy of the water because of that change in temperature. And so let's look at the differential of the enthalpy of water. And so we're going to have an area multiplied by a length by a heat capacity. Let's just get rid of those dots. For that liquid water. And then this is how the temperature becomes involved, is that differential of the temperature of the water. But what else causes the change in temperature would be evaporation. And so you could equate that to a specific area multiplied by that heat transfer coefficient, by that temperature of the gas minus the temperature of the water times the area times that differential of the distance, the length. So what we're looking at here is these variables. We already looked at this. This is the volume multiplied by that specific area that will give us our surface area involved. But then what we also want to look at is the heat transfer from air to water. So we will add a subtraction sign, and I'll explain that in a second. But this is also what I want to say is that the rate of this is the rate at which the enthalpy is changing. So now we're looking at the involvement. So this was the evaporation, and now this is going to be that heat transfer between the air and the water. And so we're going to have that heat of vaporization, that molar flux, remember, of the water that we did before, that specific area, and that change in distance. So that would be our volume. And this is the molar flux of the water interface to the air. And what this part is, this is going to be the heat transfer from the gas phase up to the water. And so we get that we get that subtraction sign because the temperature of the water is going to go down as the water evaporates. So we have that heat transfer and that cooling. So now what I want to do is I first want to divide everything by dz. And move some of the parts of this equation around. So divide everything over here and here by dz. So then we're left with that the differential in temperature of the water over, then we have that dz. And now these areas are going to cancel. And then I'm going to move this length and heat capacity of the water over. And so then what I'm left with is leaving these constant, pulling these out of the main, of grouping these. So we're going to pull that out as a constant. and then move these over, so length and that heat capacity. And we're pulling this, put this out, oh, I already talked about that, and, oops. And then in the parentheses, we want to put that heat transfer coefficient, that temperature difference from the gas to the water, and that heat of vaporization, and that molar flux of the water at that interface. And now we want to consider the enthalpy coming out, in and out of the region of a column, and there's some enthalpy associated with the water going down and the air going up, and that's going to be in joules per second. And so what I want to look at is that volume, let's say, or that region of the column like we did earlier. And so we're going to have some enthalpy of gas going up, and then we're going to have some enthalpy of water going down. So like that association that I was saying, enthalpy associated with that gas moving or that water moving. And so this is going to be in steady state, which is important. So the question is, what's that net enthalpy going down? Well, the net enthalpy going down is going to be that HW, so that enthalpy of water minus the enthalpy of the gas. And that's going to be the same coming in and out of this region of the column. And so the net enthalpy going in and out must be the same because it is at steady state. And the change in this net enthalpy going down can be described as this. Because of that steady state. So what that means is that this differential of the enthalpy of the water is going to equal that differential of the enthalpy of the gas, and that's just the change in enthalpy of the air, and then this is the change in enthalpy of the water. And this is important because we already know this this change in enthalpy of the water. Let's see, where is it? Here it is. So that's crucial. So now what I want to look at is looking at the enthalpy that is the enthalpy of the air that is coming from two different places. So let's look at it this way. So we have this area times that gas flow rate times that heat capacity of the gas multiplied by that temperature of the gas, and this is looking at the gas flow rate in particular. And now we want to look at that water vapor that brings enthalpy as well. So that's why I'm adding it, which is going to have that heat of vaporization, that gas flow rate times the area all over the molecular weight, the average molecular weight, and multiplied by that mole fraction. Because this is going to be the total moles of moles per second of the gas phase, and multiplying it by that mole fraction of the water is to get that water vapor component. And then all of this together is the enthalpy of the gas phase. So we're going to take the derivative of it. And this differential, this is going to be the differential change of enthalpy in the gas phase. And so now we want to set this the enthalpy of the gas phase. So this just equals that variable. So now we want to set it equal to that differential of the change in enthalpy of the water. And we have that up here. So this part. So let me copy that down here. Let's rewrite that. Okay, so we have, first of all, this. Okay, I want to get rid of this, actually. Oops. Where'd it go? Draw. Set it equal to that specific area multiplied by that heat transfer coefficient, temperature of the gas minus the temperature of the water times the area of the distance, heat of vaporization, molar flux multiplied by that specific area, and dz. So that volume, and that gives you the surface area. And so what I can do is I can cancel out all of these areas. And then I'm going to look for the constants that we want to keep so that we can pull them out. So kind of like before, we want to keep these constant for the same reason as before. Make it a little bit easier. Don't have to do product rule. Same thing here. Pull that out in front of that derivative. Same with this is going to be constant. And then we're going to just rework this. So we're left with the gas flow rate multiplied by the heat capacity of the gas multiplied by that difference in the temperature of the gas over distance. Then we're going to add this out in front. Dy over dz, because we're going to divide all this by dz. We have the specific area multiplied by that heat transfer. And the same thing over here, that the temperature of the gas minus the temperature of the water minus the heat of vaporization, multiply that by that molar flux at the interface by that specific area. And so now looking at this, we already know the change in the mole fraction. We already did that. So what that is that equals the negative specific area multiplied by that molecular weight over the gas flow rate multiplied by that molar flux. And this is good because now this will cancel out some other variables. So it will get rid of these and this, and it will also get rid of these over here. So these will all cancel out. So now we are left with a final, let's just change the color. We're left with a final equation that's simplified to that differential in temperature of the gas, that distance of z, specific area, heat transfer coefficient, gas over the gas flow rate, the heat capacity of the gas, multiplied by that temperature driving force, that temperature of the gas minus the temperature of the water. So now we have those three differential equations. So what else do we need from this problem is the real question. So we have the velocity of air, and that's going to be 5 meters per second. So given this this quantity, we are able to also find the gas flow rate of air. And the gas flow rate of air is in kilograms per meter squared per second. And so what would I need to find that is I would need the density multiplied by the velocity, because that density is going to be in kilograms per meters cubed. And if you multiply that by velocity, it's just that meters per second. That will give you the kilograms per meter squared per second. And so then what we could also do is we could write the density as that pressure multiplied by the molecular weight of air over that gas constant multiplied by the temperature of that feed air. And that gives us that density, and multiply that by velocity. So then what we also need is we're going to need the total gas flow rate. That's what we are interested in. So that's just going to be the gas flow rate of the air with the gas flow rate of that water vapor. And now we can put these in terms of mole fraction. And what I mean by that is just putting the gas flow rate of the air over the molecular weight of the air, and that will give us the moles per meter squared per second, and then put that all over the gas flow rate of the H2O over the molecular weight of H2O, and then that will give us our moles per meter squared per second of that water vapor. Set that equal to 1 minus that mole fraction of the water vapor, because that will give us our mole fraction for the air, and multiply that by the total gas flow rate, and then put that over the mole fraction times the total gas flow rate, because that will give us our gas flow rate for the water vapor. And so we cancel out these g's, and we can rewrite it as G air H2O GH2O. So that equal to that 1 minus y over that y. So now we know the velocity of the air and the gas flow rate of the air, and we're interested in that total gas flow rate. And then we found, so since we found that gas flow rate of the air, now what we need is that gas flow rate of the water vapor. So now I can put that also in terms of mole fractions, and write this gas flow rate of H2O, that water vapor, and just put it as y over 1 minus y multiplied by that gas flow rate of air multiplied by the molecular weight, of air, of H2O, and then put that over the molecular weight of air, and then that will give us our gas flow rate for the water vapor. And then what we do is we just plug this all the way back in to get our total gas flow rate, which we are interested in.